hello, hello. Hello, hello. 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 Hello, hello. Hello, 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 hello.
all of you know about integral. Yes? Integral. And you know, I'm sure that you did in your courses mathematics. For calculating the area under a curve. Yes, you make it like some trapezoidals or some rectangular, and then calculate the area of each them, and you then make the sum, and then become the for example, this is the curve, and somebody told you we need the area under this curve. If you have the equation, then you can make an integral analytically calculate the area under this curve. For example, they told you we want the area from here to here. If you have the equation of this curve, you can make, for example, this is x and this is y, and the y equals fx. So you can calculate the area from a to b by integral. Integral a b. Yes, we know what it is. But if this function is so much hard that you cannot make an integral from it analytically, I mean the rules that we have from integral is in a way that you cannot make an integral from that, then you will use a numerical method. What you do, you make it in this curve as a smaller part, and then you make it as some trapezoidals or some rectangulars. And now these rectangulars or trapezoidals, you can calculate their area because you know it from the mathematics. It's easy. So if you calculate all of them and make the sum, then you have the area under this curve. And you in other way you make the integral. This is the simplest numerical method for making integral from the differential equation, because this, you see, this is somehow the integral of this, and in this way you can calculate the integral. This is the base of one of the basic numerical methods that we learned before. And now we will talk more about this kind of thing here. Yesterday we talked about the basics of the model and the introduction to the modeling, and we said that model could be a very simple equation like y equals multiplied by x to very complicated partial differential equation that we cannot solve analytically, and we need to use numerical methods to solve it. Here in the next slide, and we talk about different characteristics of the model like scale and everything. Now we are going to know how we can solve that numerical model. We assume that we have a good mathematics and we make a partial differential equation of movement of the water in the river. We go to the center of the equation. Now we have our science and our knowledge. We make almost all the governing equation for the movement of the water, movement of the pollutants into the river. We have there are some partial differential equations because it said yesterday, if we look bulky and use system approach, then we have algebraic formula. But if we go to the field study, not the more details, and we use the then we have some partial differential equations, which is harder to solve them, and which is, but they give more details to us, and we can have more information about the result. If anybody has some doubt about this subject, please ask, because yesterday I understood that some of you have not some deep insight into the subject, because these subjects and these definitions are the base of the other part of the topic. So if you have any question, please don't hesitate and ask. We will describe, and I can make some examples, then we will have more details. So we have complete information here now, there is no problem. Okay. So we will go to the next step. Now we reach to a point that we have an equation for solving the for water movement, for pollutant transport. How we can solve this is a partial differential equation, and we want to know how we can solve this problem. I give you a very simple example before going to the because you see this equation before. If your measure is water, then you know this formula. What is this? Have you seen this formula before in the open channel hydraulic? This is the governing equation for gradually varying flow. Example: consider a tunnel, a channel. It reaches to the end, and the water comes from here and goes down. This formula shows us the water profile. How is the water surface? For example, if you make a dam here, if you make a dam in front of the this here, what will happen? The water starts to go high, 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 and from here it starts again down, come down, and we have such a profile. You had it in open channel hydraulics. The people who had the base in water engineering, and they had courses in open channel hydraulics, then they should know about this subject. But the governing equation for that is this one. If you want to have how is the water table before this gate, how it changed, then you should solve this equation. Yes, you should solve this equation. And for this, you must make an integral from this. Then you will have y as a function of x. If you can make a numerical, make an analytical integral from this, then you will have a y as a function of x. Then you solve the problem, and you can exactly say how is the water profile behind the gate. How many of you know this equation? Okay, so this is an example. This is a water profile. We want and the formula, the governing equation for this water table is not important, even if you know it. I'm telling you that. This is the water. If you make a dam in the river, you want to see how is the water, the surface of the water behind the dam. How would be the profile of the water behind the dam? To know this, you must solve this equation. Okay? And to solve this equation, you need to use numerical method again, because this equation is not a simple equation. You don't look at this because this S index F is a slope of the energy, and it is itself is a function of y and x. And also this fraud number, you know the fraud number. Again, the fraud number is a function of y, which y again is a function of x. So it's a complicated formula. Then we cannot make an integral from this easily from the analytical methods. We need to use numerical methods to solve this. So we will have such problems. We have some differential equations, which is the answer of our questions. But we need to solve them and make an integral on them to get the result. This chart show us how many methods we have to make to answer our question. We have two methods. One, analytical solution that you have already passed some methods in your mathematical courses, and if you go to PhD, which is more related to the hybrid, then you will learn more about some other methods like integral transform, like Fourier and Laplace methods. In PhD, we had some courses that we learned how to use Fourier series to solve and answer differential equations and make an analytical solution for them. There are some other methods like integral solutions, like separation of variables. So there are different analytical solutions, and there are some numerical methods, which is nowadays one of the most important methods that you are using. But maybe some of you later go and work so much with groundwater modeling, but you never also know this, because I saw some people, especially in Germany, because they have a base mostly on the geology, then they don't know details about this kind of methods, but they use Preflow, for example, which is using finite element method for solving the equations. And not necessarily, we have to necessarily is not. It's better that you know before you use software. If you know how, for example, I also not familiar with finite element method. I know finite difference method very well, but I don't know finite element method and finite value details. Maybe some concept about it, but it is better when you know how it's working. Then you can work with software more professional and better. For numerical techniques, we have finite difference method, finite value method, and finite element method, which some of them have again some advantages and some disadvantages, and some of them are good for some works and some of them are for other works. For example, Fluent use finite element method also, and Preflow use finite element method also to calculate. But the main idea of all these numerical methods is based on this very simple example that I told you. When we come to model a groundwater system or a river, we have a medium, yes, and we had a field approach. Do you remember this version? In the first slide we had field approach and system approach, yes. System approach consider only this room as a valve system, and we only see what is the entrance and what is it going outside. He didn't look inside it happen. But when you are going to the field approach, you will see all the particles in the in this room, and we analyze this. But when we want to do a numerical method, we cannot consider this as a continuum system, like this curve. You know, if you consider here as a continuum, then when you reach this curve, a lot of pixels. But in numerical methods, because we cannot go and consider this as a continuous medium, we consider it as a this separation separated system. We make it some points, 1, 2, 3, 4, and we consider a line as 1,000 dots, for example, 1,000 dots or 2,000 dots. If we make a space between each other, then we have a whole number. I will show you in the next slide, and then we will understand it better. This definition or this concept that I was talking about it in numerical method is discretization. I mean, it means that you have a medium. For example, you have a in this line is better. When you know line is from infinitive number of infinitive number of dots, and when you use analytical method, you solve the equation in an infinitive manner. You mean you didn't consider the dots, but when you are using numerical methods, you don't solve the problem on all dots and in infinitive matter. You solve it only in some specific dots. For example, this line has infinitive dots, but when we use numerical method to calculate the integral, we only solve this on 1, 2, 3, 4, 5, 6, 7, 8, 9. Only you will have 9 points. Or for example, for this dam that I have here, we make a gate here, and then we have a water profile behind it. If you use a numerical method, you don't find this line. You will find the results of some points. Here, here, here. You will find the depths in some points with the distance of delta x. Okay, so this is very important part of the numerical model. Discretization. Is it clear, the meaning? I will make some example later. For example, you can it's not what we assume. For example, this is a groundwater body, and you are looking it from the top, and you want to make a two-dimensional model of a groundwater model when you are looking it from the top. You can have some wells here, and it can be a groundwater model. When you want to make and you want to use one of the Darcy-based equations for solving this groundwater system, to know how is the groundwater table changed and how pollutant transport happens, you can use FIFLO or whatever. What FIFLO is doing, at first it comes and make it like some grids, okay, and then afterward it will solve the equation on these points, on these points, not in the middle. Then after that you have answered the questions only on these points, but it is sufficient for us, because we always try to consider these steps small enough that have a good description afterward about what happens to the system. But how we can make these grids? This is also, this numerical method itself is a science. I mean that it's, if you go to the mathematics, it's a subject itself. You know, a lot of people work on it, how we can work it, and you will see methods for making the medium and make it in different fields. And I will give some example. For example, the grid can be structured like this, or can be unstructured grid like this. You know, it's not it's not follow a very detailed you cannot predict how it is, but it's usually nowadays this one is more used, because with this method you can understand where it is more important for you, and you make more detailed grids, or you can, in some parts you can make your grid bigger. So it is the unstructured, and in practice we're used much more, but for education and for learning the numerical methods, we will usually start with the structured grid, because it is much more easier. To have a better feeling, if our change is only in one direction, only in X, this one was two-dimensional. So the grids are like a square. But if our change is only on a line, for example, if you are modeling a river in a one-dimensional method, so you have only X which is changing. So your grid would be like the example here. You see, we have only delta X. Yes, because the change is only in the X direction. So we have some dots only. We don't have a square. We don't have some dots. But again here you can have equally spaced grids, or you can have unequally spaced. You see, delta X1 is not equal. It's very important, you know, because when you are using a numerical models, it's not like you should view. Yes, you are using the computers. The computers are fast, but usually the numerical methods are very and our equations are very complicated, and sometimes it takes a lot of time. So if you have less grid, then you have a faster results, because sometimes in some cases maybe your computer should work 2 months to get one run, and you see what happens. You want to make a model, especially when you go to Navier-Stokes equations, it's very complicated. So for 10 seconds, maybe it works 1 week, and it say to you 10 seconds later what happens. So if you want to know 10 seconds later what happens, your computer should work 2 weeks to say you what happens. So it's important, if you can have a less numbers of grids, then it is much more faster. But the problem is that you cannot make them big so much, because if you make them big, then the result will be wrong, because the assumptions that you have will be loose. It is like this. For example, if you consider here only 3 points instead of these points that or only 2 points, this point and this point, and consider this as a trapezoidal, then your error would be this, because you don't consider this part. You will have error. So if you make your distance so much big, then you will have some error, and you cannot calculate the integral precisely. So it is important to have a smaller grids. When the grids are smaller, then your results is much more. And why it is good, this unequally? Because you will see, if, for example, if my curve here, if you consider this curve, in this part we have a lot of change. Yes, so we make the delta X smaller. But here we don't have so much change. We can make more delta X, because there is not so much error. So you can see, because when you are professional in your work, you know where the change is much more and where the change is much less. So in the places that you have a less change in your data, you can make a bigger grids, and the places that it is less change, then you can make a when the changes are so much, then you can make a smaller grids. Then your result is more precise. These stories that I am telling can work also for time steps, because we have two kind of change: spatial change and time change. So again, in the time also we can have equal grids or unequal space grid. In this slide, we are seeing the cycle of mathematical modeling. How is the procedure of mathematical modeling and what kind of error we will have. Of course, we will have some errors because we don't use analytical method. We are using assumptions, you know. We assume that this curve is a line. In this part is between the grids, we assume that the changes are linear. We don't consider it as a curve. Between the grids, we consider the change as a line. Okay, so of course there are some errors in this part. So we are starting from here, physical system or problem description. At first, you will have a description about the physical of your phenomena that you are going to model it, and from that you are going to mathematical formulation. You have, for example, this story that we have here, the water behind the dam. Okay, this is the physical problem. We have a definition and understanding from it, and when we make a mathematical model of this, this mathematical model itself will have some errors. So we have the possible errors due to the modeling. When you do modeling and when you make for example, Manning equation, the Manning is a formula that we produce. It is not a real answer to the question, yes, to the physical problems. Itself cannot, even if you solve it very exactly, it cannot say what is in the real, yes. Again, this equation also. This equation is to calculate the SF, we use Manning equation. Manning equation is an empirical equation. It has error. So even if you solve this equation analytically, very precise, again it cannot say you what is real, because this is a model. And this model and all models or formula that we have in the physics are based on some assumptions, yes. And the assumptions make errors. When you assume something, you consider you will eliminate something. So of course you will have some errors. So this is the first error that we have when you are doing mathematical modeling. After that, we are going from a continuous medium. Now we are going to the solving problems. When we are starting to solve, which kind of error we start to have. If you can solve it analytically, then you have no error, because but it depends. If you completely, if you don't change and if you don't add any assumption when you are solving analytically, then there is no error. But maybe again also you made some assumption to make it easier to solve, then of course we have some error even in the analytical solution. But in the numerical solution, at first you make this curve consists of some lines, yes. Instead of curve, you will have 1000 lines, yes. So this is the first error, the error that comes from discretization, yes. It depends. Maybe it is a finite difference, maybe it is finite volume, or maybe finite element. All of them have some errors when you make it. And then you see here we write it possible error due to possible error due to discretization, and some when you are applying the solutions. After you make it discretize, it's some error at the start, and then you are going to solve. When you make it discretize, your equation from differential equations start to become some algebra formula, and then you are going to solve them. And usually you need to solve them again by trial and error, because it's again you have 10,000 equation with 10,000 unknown parameters. It becomes such a thing, and then you need to solve it again numerically with trial and error. So again you will have some errors to the numerical method and the things that you are doing. So the solution of the numerical method again introduce some error to the system. And after you have the solution, then you visualize them and to see if it is okay or not, and then you come back again to make your error, because you will find some errors and you need to change some you should review your description of the conceptual of the physical properties, and again maybe revise your numeric model, and again revise whatever things that you have. You do have a circulation, then you get reach to the efficient and the optimized answer to your question. But it is not very bad as we are describing here. Usually we can get to a good result with a acceptable result that they can help us in our engineering aims and objectives. Okay. Here it is more general. The previous slide was only about finite difference and partial differential equation. But here again we come back to the model. I again emphasize that the model can be a simple equation to a very complicated equation. The simplest one, maybe you can solve it in 2 minutes, and more complicated, maybe take several months to overcome it. But even it is the simplest equation and simplest modeling that I can remind you is the formula for discharge over a weir. Do you remember? Can anybody tell me what is the formula for calculating the discharge over a rectangular weir? It's very easy. We have a weir, and the depth of the water on this weir is 15 centimeter. We want to see how much is the discharge which going from this weir. Do you know what is weir? With the plate that we put in front of the water, and the water goes through it. You don't know? The formula is very easy. I think you don't know. You cannot understand my what I mean. Otherwise, you should know it, because it's not very complicated. Do you know? One of you tell me what is weir? Weir. Dr. Prasad showed us yesterday. We went on the top.
It's a structure to raise the water level.
And we can also measure the discharge, yes? And what is the formula of the discharge?
It's CDLH 3/2.
Oh, yes. I was sure that you know it. Yes. It is Q. This is the formula of the weir, yes? If you have the head, then you can calculate the discharge. This is the simplest model in our major. But this model needs a calibration for this C, yes? This coefficient. We need to calibrate this coefficient, then we can use this. The things that I'm going to tell you is applicable for this one, which is the simplest equation, and also for all other models. When you have a model, at first you develop it mathematically, like this. We developed it mathematically, and we have the model, mathematical formulation of the problem. We are in this point. We do it mathematically. Then we need to numerical, numerical solution and coding. This one doesn't need this because it's not a numerical model. It's you can calculate everything easily in this formula. But these parts are more or less applicable. When the model is simpler, then maybe some part of it becomes simpler. But the total idea is the same. So here, computer implementation phase for calculation. For this, we don't need. We can even calculate with a calculator or with Excel file, whatever you can calculate. If you have H, you can put it and you can calculate Q. But for using the when we develop a formula, at first we should see if it is validate or not. If you have experience with formula and making formula, we usually, after we make formula, we check it, if it is true or not. When we develop a formula mathematically and from Bernoulli theorem and everything, for example, here, the first validation of this is that we should put H equals to 0 and we see if the Q becomes 0 or not. Because if this mathematical model is true, so in some very certain cases it must have a if we put H equals 0 and we have a small discharge, then it shows that this mathematical formula that we developed is wrong because it cannot answer to the boundary conditions that we have. So this formula is valid because if I put H equals 0, then we have the Q equals 0. So for numerical model also we will do it. Before we go to other things, when you develop your code and you write your code, at first for numerical model like industrial one, we don't need to do this because they before do this and they are validate and we know that they are working well. But if you develop a numerical model yourself, first you should check it if it is working true or not. You will give some examples and you will see if the results are reasonable or not. And in some certain cases you will have a valid result or not. After you become you understand that it is valid, then you will do some sensitivity analysis to see which parameter is sensitive in this, and if about the grids, how much it is sensitive to the grid, what is the optimized grid that you must consider for solving the situation. And when you do all these things and you find the best optimized system for solving your equation, now because it's important, you know, in numerical model, if you give very big grid, then you will not have a physical results. The results are not very reasonable. But if you start to make it smaller, then you reach to the point that when you make it small, the result doesn't change so much. So this is the optimized grid. You don't need to make it smaller. You only when make it smaller, the time will become increased. So you should find the optimized grids, and after that, you are going to test an evaluation and calibration. Here we need this. At first, you must calibrate this with field data. You must have some data, and you calibrate your formula, and you find this C. Okay. For this formula, the scientists did it for us several times. Because of that, you have a lot of curves that show you, based on the characteristic of the wear, what is the number of the C. And you know it is equal 0.6 to higher. It depends on the, and the average is 0.6 for the wears. But we have a lot of graphs and everything that you can calculate the C from them, because other scientists do this work for us. Testing and evaluation and calibration for this formula. For all numerical methods, you should do this. Based on your data that you have, you should calibrate them. If you have 1,000 data, you will use 300 of it for calibration part, or maybe for 700 of it for calibration part. Yes, most of them should be used for calibration part. And then after you calibrate your model, Now you must test it if he always can make a good answer or not. This is verification part, because you want to say to the water authority that you can from now use this model to understand how is the pollutant change in the groundwater. You must be sure that, because yes, when you calibrate with your data, the result of the model with the calibration with the data is completely good, because you calibrate the model with this data. So I mean, if you have 10 water depths and 10 discharge and calibrate with this formula, of course this formula, and you bring the C equals to 0.7, then of course this formula was for this data have a good result. Yes, if you test them again, they are good. But you must test with new data. You should go to field again and get some data and check if the model can have a good data or not. Because of that, when you have some data, we make it two part. Some part we use randomly. We use some part, for example, if we have 1,000 data, we get 700 of these for calibration part, and we make calibrate, and we find the C. Here as an example, but for example, for pollutant transport, we need to see the decay process, we need to know the coefficient for the dispersion, advection, no, we know it, velocity, check the velocity, and other things, and also for sorption, for example, we need to know the coefficient of the sorption, maximum capacity. We should consider all these things with our data that we have and calibrate it. Then we have 300 data that we will use them for verification part to see if the model really can predict the things true or not. Now we are sure that this model for this case study can work perfect. So we can say to the others that you can use this model for predicting what will happen in the future, what will happen if you change your policies. You can use the model now and you can trust the model. So it is application. And also post-processing, it means that we need again, after a while, we have some data again to check if the models are going well or not. And we modify our model with the time. So this part is finished. We came back to our first slide from the course, because we are going to talk about now pollutant modeling. How we can model the transport of the pollutants inside the environment, and what is the important factors and how we can consider them. Now we know the basic of the modeling. We know for each phenomena that we are going to model, at first we should have an insight from the physical happenings, and from these we should develop a mathematical model, and then we solve the mathematical model. At first we should focus on the physical concept and to see what is the process that control the things that we are trying to model it. For example, at first, again, I go to this example, for example, because it is easy. If we start from the easier one, then we understand better the complicated one. For example, the water table changed behind the dam. This is the gradually varied flow. Yes, we know it. If you put something in front of the river dam, the water table comes high, and we will have a profile. What is the name of this profile? M1. If the slope is mild, then we have M1 profile. Yes, because if there is a water falls down, then this is M2. Yes, the water will. You don't have these profiles, and yes, M2. Okay, so we want to model this profile. At first, we should look at this, and we will see what is the governing equation on this, and what affect this water table. And then, when we release the process that happens and start to define them mathematically, then we will reach to an equation like this. That if we solve it, then we can model the water table, and we calculate the water table behind it. Again, for the pollution, our main concern is that always our water bodies, which can be a lake, which can be a river, which can be a groundwater, which can be a sea or ocean, always subjected to pollutants. Some pollutants come to our water body. For example, here, this is a river. Okay, this river, this factory put his water here. Put his wastewater inside the river. Again, when we have rain, we have a runoff from these agricultural lands to the sea, to the river. We have from this agricultural land to here. We have a wastewater plant here. He put all the materials inside these. We have another farm here. They use pesticides, so their runoff goes to the river. For us, as a engineer and as a person who want to water model, what is our objective? What we want to know? Again, this is another example, but I like this example more. What if you are a person who are working in a water authority? What is important for you? You want to know how is the change of the parameters that we are talking so far. We had lots of parameters. We want to know, for example, if we have here, no, but we can create it. For example, here you are deciding to get water and bring for making a drinking water for a village. Yes, you are a water authority. And you heard that some of the village, they don't have enough water, and you need to make a here something and get the water from this river to the to them. For you as a water authority, is important to know how is the concentration change here. Yes, for example, the BOD during the year, how is it changing? You don't want to put a sensor here and you see. Yes, you can put the sensor here, but you have some data for every month. You don't have details. And more importantly, we want to see if I say to this factory, reduce his pollutions into the river, how much would be the here, you know? Or more practical, I want to make a plan for them and tell them, you must put only 1 ppm. You can put 2 ppm. There is no problem, because your position is in a way that if you put even 2 ppm, nothing happens. Or you must do like this. And maybe I can give them plan. Tell to the farmers, please do, for example, 2 days sooner nitrate application or 2 days later. Because before, if I can make a plan, say to this farmer, at first you start, then you start to make the nitrate, then we have a time gaps in the pollutants that comes to the river, then we can control. These are strategies. These are only as example. A lot of things. For this, I need a model to say me when these things change, how water pollutant movement through here will change. Yes? This is our objective. We should make a model that can tell us what happens. For this, at first we should know what is the governing process for solute transport. When something comes to the river or to the groundwater, what is the main process that affects its fate? What happens to him? Yes, this is our questions. We should from today we are trying to find the main process and main governing equations for this. And unfortunately, for pollutant transport, there are several parameters, and we will discuss about them. And then at the end, we will reach to some point that how we can model. We are going now to discuss about this process. What kind of process will affect the movement into the river or groundwater? Some of them are the same. I mean, some of the process are is in both of them, in the groundwater and in the river the same. Some of them are special maybe for groundwater, some of them may be special for rivers, but there are several, but we should know them before we start to model. We should list them, how many items we have. But of course, all these processes are not the same for the all pollutants. Maybe some of the pollutants have some of these process, or some of them has more, you know, it depends. And in some pollutants, some of them are not very important. We can omit them. We should see the situation and we will discuss about them. And I will tell you how should you decide finally which kind of these process should be considered in your model when you are modeling something, because this is important. You never can model all this process, and it is not economical. For example, if we have 20 process then that can affect the pollutant transport, and you are going to model the transport of cadmium in one river, you mustn't put all these 20 process in your model for cadmium. You should choose which of them are important for cadmium and for the situation and for the physical situation of the water body that you are going to model it. This is another example of the pollutants that comes. We have gasoline sometimes that goes to the groundwater system, and everyone. This is similar to that one. We can pass it. In this slide, I am talking to one of the concerns. The previous example was about the river. Here we talk about the groundwater. And also another important one. You know, usually groundwater, and especially in India, this is the case. Maybe in Iran it is not very the case, because our groundwater system is very deep, more than 100 meters, and it's far from the river. Sometimes they are not very connected to each other. Of course, again, they are connected when they are near the river, but it is reverse. The river recharge the groundwater, but when they are very close to each other, then they affect so much. If a groundwater table comes a little bit lower, something happen. If it is going a little bit higher in the winter, again, something else happen. But in Iran, it's always the same. Always the river recharge the groundwater. So the direction is the constant. But for example, if we see this system, we have a farm here. It start to send the water. The pollutants are leached to the toward the groundwater. There are several processes that we should consider how these leaching solutes go towards the groundwater, and when it reaches the groundwater, how it moves. Because you see, we have three medium: groundwater, capillary fringe, and the vadozone. Here is completely unsaturated. Here and here is between unsaturated and saturated, because it's more saturated, and it is completely saturated. And so different the movement here with here completely different. And nowadays the research that we are doing, and I will explain more, we understood that this capillary fringe also plays an important role in traditional way, we assume that the groundwater table, solutes go directly vertically to the groundwater, and when it reaches to the groundwater, it moves horizontally. But it is not like this. When the here it goes vertically, but when it reaches to the capillary fringe, it starts to move horizontal. So here also there are some process that happens. We should consider this if we want to be in details what happens about it. Then we have the groundwater surface water interaction here. The river have affected. The amount of oxygen here, and here are completely different. So the bacteria and other things that affect the pollutant transport are different. The distance of the farms can be different. If the farm is much more farther from the river, it will change. So what is the effect of the distance from the farms? For us, it is important to know how this, if we inject from here, how it moves to here. And then we have the plumb, and we can understand and predict what will happen. And again, why it is important? When the pest here, when they comes to the groundwater, they start to move, and depending of the solutes, the kind of solutes, the distance that they are going are different. For example, here phenol will move 416 meter approximately into the groundwater. So from the place that you inject it till 416 meter, you can see it. This is the mean transport length of organic substances in groundwater. Aliphatic chlorinated hydrocarbons, 1,543 meter. So this is also for us important. If you know how much length the pollutants move into the groundwater. And you have other substances just like PAH, 277, like other substances around 800 meter. This is the length of the, or for example for benzol, we have 209 meter. So each pollutant had different lengths that they can move through the groundwater table, through the groundwater. But what is the we can see it here. What is the how in this slide we can see how when you inject a pollutant into the groundwater, it is an experimental laboratory. We can see how when we inject pollutant start to move inside the groundwater. Is it showing? Yeah. You see we injected here and here. You see how the pollutant start to move, and you see they are completely different. The one who is downer with the one, it is completely different with the one who is upward. And if you have a well here and you start to pump water, then you get all the pollutant inside your well, in the water that you are put the pollutant here, and you will start to use all the pollutant that he injected to here. So you will see how the pollutant start to move here, and we are going to understand the governing equations for that, and to see what is the main factors that affect this transport to see. Okay, it is not finished. We will see it again because it start to inject another one. You see, I'm not talking that, then you can concentrate on to see how it moves. The groundwater table is here and here. And you can see the time also. Yes, yes. So,
These are piezometers.
but this is experimental one. It's a,
Vertical, these are piezometers.
these are
lines.
these lines are like wells. They representing wells, not completely. They make some holes. You see, inject another pollutant from here. It's finished. Okay, we can have a rest and we will continue after. And if you have questions you can ask me.
Have there mobility factor was
What?
mobility factor for different compounds?
Mobility factor? Yes. I cannot understand your meaning. Sorry. Mobility?
So different compound having different type of mobility factor, like as a movement. When sir any compound combined with other complex metal, they formation of big compound. And
Then slower. Yes. The previous slide that I show you is sorry.